We're going to explore the evidence that supports the theory of plate tectonics in this video. And we're going to approach this like true scientists would. We're going to examine the evidence that became apparent to those that were investigating this, and we're going to follow that evidence trail to its logical conclusion to see where it takes us. So we're going to do that evidence inquiry based on two main questions. What is the evidence and what does it suggest to you? If you've ever sat in a geography classroom and looked at a map of the world, you may well have noticed that some of the continents appear to be made to fit together, particularly South America and Africa. But when you bring in North America and Europe, there's the British Isles, and there's Greenland in there. Actually, you can make these fit together very, very snugly. And especially when you go not just to the coastlines, but to the continental shelf. That's the area of continental lithosphere that sticks out a little bit underneath the ocean. There's an even greater match between those. These do look like they were meant to fit together. And it was our good friend and hero in this story, Alfred Wagner, that really came up with the start of what ultimately became the theory of plate tectonics. Whenever he came up with the theory of continental drift, he thought the continents were moving around the planet, and at one stage they had all been together in this supercontinent called Pangaea. And since then, the continents have moved apart. This GIF focuses particularly on the journey of India as it moves away from the South Pole up towards the collision with Asia that would form the Himalayas. But why? What was it that convinced Wagner that this theory was something that was worth pursuing? Well, we're going to break our evidence into two broad categories. We're going to start off by taking a look at the land-based evidence, and this was the evidence that Wagner saw, and we'll be asking those questions again. What is the evidence and what does it imply? We'll construct this knowledge schema on the way through. We'll take a look at the evidence. There's the land-based evidence. We'll look also at sea-based evidence. That'll take us into the theory and finishing off with the mechanism of how all of this operates. So let's take a look at the first piece of evidence. It's rock, age, type and structure. So if you move together North America, Africa, Europe, British Isles, Greenland, if you bring them together in this jigsaw-like fit, something quite significant happens. In fact, jigsaw is a good metaphor to use because the jigsaw puzzle pieces here seem to fit together, but not only do the puzzle pieces fit together, but the picture that's on them matches up. What's the picture in this case? Well, you have a mountain chain, rocks here that are running through these separated areas of the planet now that are the same age, so they were formed at the same time, but they're also the same type of rocks, so they were formed by similar processes, and they have the same structural orientation, so they look like they fit together. This absolutely suggests they were formed at the same time in the same way at the same place. So what does that imply? Well, the continents since then have moved apart, separating these rocks, but ultimately in the past, these rocks and these continents must have been together. That's the first piece of evidence. Let's move on to the next one, the fossil distribution. Now, if we take a look at the fossil distribution across the planet, I've just got three examples here of plants and animals from the past, and we can see that we've got exactly the same animals separated here by thousands of kilometers across the Atlantic Ocean. Now, the question is, how do you get exactly the same animal here and here? You'll know from even some of the basic processes of evolution that you can have different types of animals in different continents. The marsupials, for instance, in the separated continent here of Australia have a different evolutionary history than the mammals that, say, you would have in Europe and in Africa. So if you separate continents out, you would expect the animals to be slightly different. And yet we have exactly the same animal here and here. Exactly the same animal here and here. And similarly with plants, ferns, you have them separated out by all of these thousands of miles, growing in different climatic zones even. So how do we explain the fact that the same animals are found so far apart? What does that evidence imply? Well, according to Wagner, if you brought all of those continents together in this supercontinent of Pangaea, then you actually don't have an issue, because what was far apart by thousands of kilometers is now relatively close. You can absolutely get the same animals in these locations whenever that happens. Okay, our next piece of evidence is something to do with climatology. And this time looking at fossilized polar plants and where they're found in the planet. Now we're going to link this up to the map of biomes. You'll see here, first of all, that you've got polar plants that are in the tropics. But also if you look at the biomes, this is a tropical rainforest biome, this one is a savanna biome, and this one is a desert biome. So how do you get polar plants here? Similarly, if we go to the UK and the British Isles, you can find fossilised tropical plants, even though we are way outside of the tropics. So what does that evidence imply? Well, perhaps it implies that the countries and the continents were not always at the same location that they are today. This is a globe showing the distribution of the continents on the Earth about 300 million years ago. And right in the centre there is the British Isles, and there is the equator. So if the British Isles used to be at the equator, then all of a sudden getting fossilised tropical plants here aren't anything particularly surprising. But let's take a wee look down here towards the South Pole. Now I'm going to try and help you to see where some of these continents are across the planet. There is Antarctica, there is India, there is Australia, and there is Africa. There's South Africa there. So according to the theory of plate tectonics, these continents about 300 million years ago were centered over the South Pole. And if they're centered over the South Pole, then it's very easy for you to get the polar plants growing there. And since then, they have moved away from that location, and we have moved further north. So you get this distribution now spread out all across the planet. So what does that evidence all suggest and imply? It suggests that the continents are not fixed across our planet, that there is movement over timescales of tens and hundreds of millions of years. And that was the evidence that Wagner assembled as he started to come up with the theory. But the thing that he couldn't get was the mechanism of how. It seems like an absolutely bizarre idea. We're used to it now, so it doesn't seem that crazy to us. But moving the continents across the surface of the planet, how would you even go about doing that? Now, it turns out that just looking at the continents, Wagner never could get to the mechanism, because it turns out actually it's not the continents that are moving after all. It's the seafloor that is moving. The continents just happen to sit on the seafloor, but it's the seafloor that's moving. And unless and until you see what's happening down there, it's very, very difficult, almost impossible to come up with a mechanism. So let's go on and take a little bit of a look at that seafloor evidence now. And again, the same two questions. What is the evidence and what does it imply? And this time the story brings us to this fella here called Harry Hess. He was a scientist who happened to work for the US Navy during the Second World War. And during the Second World War, there were a series of instruments that were produced to help the Allied forces in their battle against Nazi Germany, in particular in the sea, whenever the supply of provisions and food and so forth to Britain was so important during the war. The transatlantic shipping route became absolutely vital. And of course, for the Nazis, that was the thing that they wanted to attack. So they sent out their submarines, the German U-boats, underneath the water, prowling around, looking for these convoys to sink them. And the warships that were protecting the convoys were looking out for the U-boats, trying to attack them. So how do you find something that's hidden under the water? Well, here are a couple of the instruments that they used. They devised this sonar, which is kind of like a sound-based radar, which operates underneath the water. You send this out, and whatever it bounces off something, it sends these waves back down and it lets you see what's underneath the water. This one is a magnetometer, so you can read the magnetic fields that are being produced by the U-boats underneath the water as well. So these two devices helped these Navy operatives find out what's underneath the water. But Harry Hess, who was there, he was also a scientist. So he was able, during the war, and particularly after the war, to find some other use for these, to begin to see what the seafloor was like. Which brings us then to our next piece of evidence. As Harry Hess and others started to collect this data, collect this information, what did they discover? Well, the first thing that they discovered was this ocean floor relief. And they discovered that underneath the ocean floor, there are these incredible patterns in some of the topography waiting to be discovered.
The Mid-Ocean Ridge, a vast underwater mountain range, riven with gorges that would dwarf the Grand Canyon and studded with mountains taller than Everest. For 70,000 kilometers, this rugged volcanic seam snakes around the planet, stretching down from the Arctic Ocean, through the Atlantic, Southern and Indian Oceans, and all the way up the Pacific. The ridge is at its most dramatic in the Atlantic as it carves a giant S between the old world and the new. Since its discovery in the 1950s, scientists exploring the ridge have made some huge discoveries. One of the first was proving that the Earth really is moving beneath our feet and that the continents are in constant motion. At its heart is a central crevasse, a rift between plates of the Earth's crust. As these plates move apart, they expose the fiery heart of the planet. But despite the fact that up to 95% of the world's volcanic activity occurs on the ridge, almost no eruptions have ever been witnessed here, let alone studied or sampled. This film from an eruption more than a kilometre deep off Samoa is one of the very few records we have. Off Brazil, at the remote St. Peter and St. Paul archipelago, the geological forces are so extreme that they've pushed the abyssal seabed above the very surface of the sea. Scientists are now finding clues as to how life itself began. Next, they're planning to drill down towards the center of the planet in a multi-billion-dollar mission as complex and significant as landing a probe on Mars. Only a tiny proportion of this extraordinary mountain range has been visited. New species, environments, and phenomena all await discovery. That is the only certainty.
Surface, LF, depth 109.28 meters.
Okay.
Men.
Okay, roger that. We'll go for a release. That's all.
Life support, good. Depth 109.28 meters. At bottom. Repeat. At bottom.
At the bottom? Yep.
Roger, LF. Understand you are on the bottom. Congratulations, Victor. Congratulations.
Well done. Beginning exploration of the bottom.
Well done.
You did it, buddy.
Well
you
done.
did it.
We all did it. We all did it. Captain Walsh. Thank you. Thanks for showing the way. You're my hero. Thank you. No, you're mine. It was an amazing experience. It was an amazing dive. I think almost exactly 12 hours, about 3.5 down, 4 hours on the bottom. I think the longest anyone's ever been on the bottom of the Challenger Deep, and then about 4 hours up. I went through pretty much all of my electrical power and had to be swapping batteries around and circuits around. It was a great journey. Saw some really interesting things on the bottom.
And so what we see there is this emergence of these features, this mid-ocean ridge that has this big rift valley or canyon running through it, and also the trench that is found closer to the edge of some of the continents. But as more and more of this pattern emerged, then indeed a pattern began to emerge from this. This wasn't just a ridge in one location, but this was the longest continuous mountain range in the world that was stretching through most of the world's major oceans. And surrounding that, particularly here, you can see it in the Pacific Ocean, the Ring of Fire. You've got the trenches here. So there's a pattern to this topography. And anytime there's a pattern, it suggests that there's something at work producing this pattern. Take a wee look, for instance, at the shape of this ridge. Remember, our theory is that these continents were joined together once and have since been moved apart. If you notice the shape of that ridge, the shape of the ridge corresponds to the shape of the continents. Now, the continents are now hundreds and thousands of kilometers away in some cases, but the shape there matches up. So if you match those two together, finding this down in the middle of the ocean here is exactly the kind of scar that you might think would be left behind if there's some massive processes that are ripping continents apart and moving them across the sea, or moving them with the seafloor away from each other. This is exactly the kind of thing that you would expect to find. So there was this pattern to the seafloor that began to suggest, well, maybe at this point at the ridges, new lithosphere is being created and it's moving away and it's being destroyed here at these trenches where it's plunging further on down. And we begin to see the evidence for the mechanism. Now let's take that further to the next piece of evidence, to the age of the seafloor. If we have a look at this map. Now, presenting a map like this to you, it's a little bit more challenging for you to get your head around. So why don't you pause the video and see what sense you can make of it, and then I'll explain it to you. So what we have here is North America and South America. So you've got America in the center of the map, which we're not used to seeing here in Europe. You've got Africa here, Europe, and there's Australia and China. Now they're all grayed out because in this case we are interested in the patterns on the oceans. So let's start with the Atlantic Ocean. There's the shape of that ridge that we're used to seeing in the previous slide. This time it's showing you the age of the rock. So what we discover that as you move from the center of the ridge away, as distance from the ridge increases, the age of the seafloor also increases. But crucially with this, it's exactly the same on the other side. In other words, that pattern is symmetrical. Here's a little analogy for you. Have you ever painted a picture of a butterfly whenever you were in primary school? One of the ways that I used to do it, certainly, was to take the page, fold it in half. You would draw out your shape of your butterfly on half of the page, paint it, and then before the paint dried, you fold it over. And lo and behold, you have got a perfectly symmetrical butterfly. So it's almost exactly like that has happened here. What is coming out from this side is exactly the same and symmetrical as what's coming out from this side. So remember, if our theory is that new ocean floor is being created here and is pushing the old ocean floor away, that's exactly the pattern that you would expect to see. The newest ocean floor at the ridge, where the older floor is being pushed away, and the continents which are sitting on the ocean floor are being pushed apart as a result of that process as well. Okay, the next piece of seafloor evidence is something called paleomagnetism. Let's have a wee look at it. Now this is an oblique view of the ocean floor. It's almost like we're in one of those little submarines floating above the floor looking down at it at an angle. This is the magma coming up from underneath in your asthenosphere, and this is your lithosphere up here towards the top. So you've got the magma coming up in here, and as it comes up here, it creates some new crust as these plates are moving apart. Now, one of the things you need to know about magma is that it has some iron in it, and iron will respond to the magnetic field. If you've ever done a little experiment in science with the iron filings where you set them down with a bar magnet, you'll see that the iron filings will align themselves to the shape of the bar magnetic field around it. So the magma comes up with iron in it, and while it's still liquid, it aligns itself to the magnetic North Pole. That magma then cools and hardens, and that alignment is locked in, it's baked in, it's frozen in time, pointing up towards that direction. Now, let's fast forward 10, 20, 30 million years. Remember, what we're doing is moving that plate apart there and moving it apart there. So this central bit here in red, we're going to move to either side. We're going to split it apart, move it a little bit further out, and some new magma is going to come up and fill in the space. There we go. There's that magma, the red has now been split apart, and the new magma has come up to fill that gap in that place. But you'll notice that I've done something here. I've moved the bar magnet from the north to the south. Now the reason for that is because every once in a while the magnetic field of our planet flips, and the magnetic north moves from the North Pole and ends up on the South Pole, which then means that the magma that comes up into this location here, the iron in it aligns itself to the magnetic field, which is now at the south, points in that direction, cools and hardens, and that is baked in. Let's do that process again. Let us now take this bit of the seafloor, which is at the central of the ridge here. Let's split it apart. Let's move it from side to side and see what happens next. There we go. We've split it apart, moved it from side to side, and there's the new crust that's been created since then. But notice again, our magnetic field of our planet has flipped. It is now up at the North Pole. So the iron in the magma here aligns itself to the North Pole, and as it cools and hardens, it points in that direction. And so on, and so on, and so on. So what you basically get is this pattern of the magnetic orientation of the iron in the seafloor, forming these stripes of reversed orientation, pointing towards the North Pole, then pointing towards the South Pole, then pointing towards the North Pole, and so on. And again, that pattern is largely symmetrical. So what does that suggest? What's that imply? It implies that process of seafloor spreading that we thought was happening is indeed going on. Here we can see it over time. So there is your normal polarity in blue there. There's the reverse polarity when it goes down to the South Pole, and you can see this just being split apart and ending up producing these magnetic stripes. And the magnetometers that they produced to look for the German U-boats were able to read those magnetic stripes in the seafloor, and that was exactly the process or the pattern that you would expect if the process of seafloor spreading was occurring. So the final piece of evidence then is to do with the pattern of world earthquakes. And for this, we do need to actually come again to a period of war. This is now the end of the Second World War, and we're into the Cold War afterwards. The Second World War ended in part, as you know, due to the Americans dropping the atomic bombs on Japan and causing that utter devastation, which led then to the Cold War and the development of nuclear weapons. And America and the Soviet Union were trying to devise and develop even more powerful atomic weapons. And of course, you needed to test those. But this isn't something that you can test very, very easily and very subtly. So what they would have started to do was to test some of them underground, so that they couldn't be observed by satellites or planes or anything like this. They'd be exploding underground. But of course, an explosion of that size is going to send seismic waves around the planet. So in order to try and spy on each other, they set up this worldwide network of seismometers to test and see what is going on and what the other side were getting up to. And of course, they did find out about the atomic bombs that were exploded, but not just that. Of course, because seismometers will measure any kind of vibration at all on the planet, including, in this case, you have the pattern of earthquakes. Now, again, if you're living in California, you know that earthquakes are quite common there, and again down here through South America. But maybe what was not quite so apparent was all of these earthquakes that are occurring in some of these mid-ocean areas. And as the seismometers were measuring the bombs being exploded in Siberia, they also picked up all of these earthquakes around the planet. So this is the pattern of global earthquakes between 1900 and 2017. This is the ones that we managed to pick up and that we know of. And you can see again this forms a pattern. And the pattern, of course, looks extremely similar to the pattern that we see in this map. That the earthquakes tend to map onto the top of some of those topographical features. So we're going to start to assemble this evidence together. We can see the evidence of the ridge going down the centre of the ocean there, the evidence of the trenches here. We can map on top of that the age of the ocean floor, and what we can begin to see is that as distance from the ridges increases, the age of the ocean floor also increases. You can see that symmetrical pattern either side. But you come over here into the Pacific Ocean, you can see here that as the age or the distance from this ridge here up to this trench here, that you're getting an increasing age along this whole entire seafloor over the Atlantic or the Pacific Ocean. So it seems to suggest again that what we're getting here is the creation of new seafloor here, pushing that older seafloor away and away until eventually that older seafloor is destroyed at the trenches. But then we can put on our recent earthquakes. We can map that on as well. And you can see the pattern that is emerging from that, how that all matches up. It matches up onto the topography. It matches up onto the age of the seafloor that we're noticing, which allowed us then to come up with this theory of plate tectonics, because then what we can do is to put on the plate margins that exist around our planet, and through gathering all of that evidence, we discovered this network, this pattern of plate margins that go all around about our planet. So the theory then of plate tectonics came from this evidence, and it suggests that the lithosphere of our planet is not one complete whole, but it's divided up into a series of plates. And these margins, as we've just seen, are marked by these linear patterns of earthquakes and these landforms, such as the ridges and the trenches, and the pattern of the age of the seafloor, and the pattern of the paleomagnetism. And all of that then suggests that there is this mechanism going on. And the mechanism can be summarized like this: as there is heat escaping from the center of the earth, that heat rises up through the mantle, up through the asthenosphere, and it introduces heat into the system. That heat then creates the process, or leads to the process of seafloor spreading. We'll unpack that in a little bit more detail in the next section of exactly how that happens. But the seafloor spreading that occurs at the ridges that pushes the plates apart, and you're getting the subduction of the cold, older, denser plate at the trenches, which pulls the plates apart. So the plates are simultaneously being pushed apart and pulled apart, and that is your mechanism that explains the evidence that underpins the theory of plate tectonics.